This lesson is titled The First Derivative and Graphs. The purpose of this lesson is for us to learn to see how the first derivative will give us information about certain characteristics of a function, and with that information we can learn something about the shape of the graph of that function, and we can also learn about what we call relative extrema, which we will define in a second. The first definition that I want us to look at is the definition for increasing and decreasing functions. A function f is said to be increasing on an interval if for any two numbers x1 and x2 in the interval, with x1 less than x2, then f of x1 is less than f of x2. Let's see if we can dissect this part of this definition and kind of bring it into layman's terms so you can understand what they're saying. A function is said to be increasing. Increasing means it's getting bigger, doesn't it? Notice that we're picking two numbers, two x values. x1 is less than x2 is telling us that on the x-axis, x1 is to the left of x sub 2. Recall that f of x is referring to a y value. So the y value associated with our first x value is going to be less than or below the y value associated with our second x value. Now we'll go to a graph in a second and I will illustrate this a little bit better, but right now this is saying as we move from left to right with our x values, our y values are getting bigger because our first y value is smaller or below the second y value. Now, similarly, we have a definition for decreasing. A function f is said to be decreasing on an interval if for any two numbers x1 and x2 in the interval, again, x1 is less than or to the left of x sub 2. Notice this time, if our function is decreasing, our first y value is larger or is above our second y value. Now let's go to just a little blank screen here for a second, and what I want to do is sort of just randomly sketch a little bit of a graph. So we're going to have our x-axis here, our y-axis here, and let's just say that when we graph our function, it might look, this looks kind of like a sine graph, maybe part of one. Notice that from this x value right here till we get about right in here, as we move from left to right with our x values, our y values are getting bigger, aren't they? In other words, the leftmost y values are below the rightmost y values. So on this segment of our graph is increasing. Okay, you can think of it as the graph is going up as we move from left to right. Okay, now from the x value here, notice right along here on our graph starts falling as we move to the right, and it continues to fall until we get right along in here. So from this x value to this x value, as we move to the right, our y values are coming down, they're getting smaller. So we would be decreasing on this interval. Okay? Notice right along here, our graph starts going up again. So as we move from this x value this direction, our curve is increasing again. So again, it's real important, this idea of moving from left to right, just like you read a page of print, left to right. Our graph, first of all, is going up, so it's increasing. Then it's going down, so it's decreasing. And then finally it's going up again, so it's increasing. That's basically what that definition is telling you. Okay? Now, what we want to do is to do a little bit of exploring and talk about how the derivative can give us information about whether our graph is increasing or decreasing. Notice that if I pick a point, let's say somewhere along in here, and sketch in a tangent line, okay? Or if I pick a point, let's say right in here, and I sketch in a tangent line, notice that on any of these places, I'm going to sketch in one more, any of these places where the graph is going up as I move from left to right, these tangent lines will have positive slope. Recall from algebra that if a line is going up as we move from left to right, it has positive slope. So all along here, any tangent line that I were to draw in will have a positive slope. Similarly over here, all these tangent lines, even right along here, we're going to have a positive slope, aren't we? Notice, however, if I pick a point here where the graph is decreasing, if I draw in a tangent line here, it's going to have what? Negative slope. Okay? So we're going to find out that we can determine by looking at the slope of tangent lines whether our graph is increasing or decreasing. If our tangent lines have positive slope, our graph will be increasing. But if our tangent lines have negative slope, then our curve is going to be decreasing. Recall that the first derivative gives you the slope of those tangent lines. So we have here a test for increasing and decreasing functions. Notice f has to be a function that is differentiable. That means we can find its derivative on some interval. If that first derivative is greater than 0, that's saying what? It's positive. Anything greater than 0 is positive. So if our first derivative is positive for every x in that interval, then we know our function is increasing on that interval. Similarly, if our first derivative is less than 0, meaning it's negative for every x in some interval, then the function is decreasing on that interval. Finally, notice it says if the derivative is exactly equal to 0 for every x in an interval, then f is constant on that interval. Let me go back to this little sketch that we had right here. I'm just going to make up some numbers here. Let's say this was at x equal -1 right here, and let's say this is at x equal 2, maybe this is x equal 4, okay? On the interval from -1 to 2, recall how we write those intervals? My function is increasing because all of my derivatives would be positive since those tangent lines would all have positive slope. From 2 to 4 on the x-axis, between this x value and this x value, my curve is coming down. So I am decreasing there. My derivatives would all be negative because those tangent lines have negative slope. Then finally, from 4 to, I'm just going to say infinity here, assuming this keeps going up, my curve is increasing again. Now, I didn't talk about what's going on over here. Notice that right above x equal 2, the way I've sketched this graph, there would be one little point where I would have a horizontal tangent line. A horizontal tangent line would have a slope of 0, wouldn't it? Okay? Meaning the first derivative would be 0 there, wouldn't it? It's only 0 at that one point. Notice on the left-hand side of that point, my curve is coming up. On the right-hand side, my curve is going down. So right at that point, where the derivative is 0, or where that slope is 0, is where I change from increasing to decreasing. Now, the last part of this definition that was talking about a function being constant, that was implying, let's say we had a graph, and maybe our graph was increasing, and then it got right along here, and then all of a sudden it went straight across. Well, notice between here and here, my tangent lines would just lie right on that curve, and they would all have a slope of 0. So let's say if this is A and this is B, on that interval from A to B, my curve is constant. It's not going up or down, and all those slopes would be 0. So we have this test for increasing and decreasing functions. If our derivative is positive, our curve is increasing. If our derivative is negative, then our curve is decreasing. If the derivative is equal 0 for an entire interval, then the function is constant on that exact interval. Now, as I mentioned in this sketch, if our curve is increasing for a while and then it changes to decreasing, there's going to be a place where that change takes place. And so we want to explore that by looking at this definition for critical numbers. If C is in the domain of f, in other words, if f of c exists, the function is defined there, then C is a critical number of f if the derivative at C is equal 0 or the derivative at C is undefined. In that last sketch, I talked about those places where the derivative is equal 0. I'll show you in a second what we're implying here about that derivative being undefined. Remember, C is in the domain, so this is not a point of discontinuity for our function. Our function is definitely defined there. Now, let's talk about continuous functions. That means there's no break. If f is continuous, then the derivative, f prime, can change sign, that means go from positive to negative or vice versa, only at critical numbers of the function. So, if f is continuous, we will use critical numbers to define what we call test intervals. I'll illustrate this with an example in a second. We will find the sign of the derivative at an arbitrary point in each test interval to determine whether f is increasing or decreasing on that interval. Now, I'm going to kind of start over with another sketch, and we're going to talk a little bit about what that just told me. So again, let's say we're coming up, and then we go down, and then we maybe start over again. Right at this point right here, I'm going to have a horizontal tangent line. My derivative is going to equal 0. Okay? At that point is where my curve is changing from increasing to decreasing. Now, between that point and the next place right along here where I have a horizontal tangent line, in between there, notice the curve is continually decreasing. I can't go from decreasing to increasing unless I go through one of these sort of level places. Now, there is another type of situation that can occur. You can have a graph that comes down, and I'm going to draw in something that looks sort of like that absolute value function graph, if you remember that thing. Notice this little sharp corner. Notice my curve is decreasing till I get to here, and it's increasing after that point. Now, right at that point, the derivative is undefined. That's because we're not making a smooth transition there. So there's no tangent line at that point. Okay? If you were to look at the limit, if you go back to your definition of a derivative and look at the limit, that limit will not exist there. So if our function does not have breaks in it, we can change from increasing to decreasing or decreasing to increasing only if we go through a place where our derivative is 0, we've got that horizontal tangent line, or we go through a place like this that has a sharp corner. In that case, the derivative is not defined. We sometimes refer to that as a cusp. Sometimes, too, curves might come down like this and go back up like that. We're decreasing here, we're increasing here. Notice that real sharp little point there. Even though you're not coming in like this sharp corner, right at that sharp corner again, the derivative is not defined. Now, we're going to look at a definition for relative extrema. If there's an open interval in which f of c is a maximum, that means the biggest point, then f of c is called a relative maximum. Similarly, if there's an open interval in which f of c is a minimum, then f of c is called a relative minimum, okay, a low point. This is the important thing. If f has a relative maximum or relative minimum at x equals c, then c is a critical number of f. Look back at this graph. There's an interval where this is a high point. Now, eventually this graph is going to keep getting larger, but right in here, between, say, here and here, that's a high point. This is what he's referring to as a relative maximum. Notice right in here I've got a low point. So in this interval, that's a low point. This is a relative minimum. Notice here I have a horizontal tangent line at that relative maximum. So this was a place where the derivative is 0, and according to our definition of critical number, that makes this a critical number, this C value right here. Right here, again, I've got a horizontal tangent line. The derivative is 0 at this x value. So again, that would be a critical number because the derivative is 0 there. Notice here the derivative is undefined. That's a relative minimum. It's a low point. The derivative is undefined there. Recall that your definition of a critical number, I'm going to put it back up here. Our function exists there. The derivative is either 0 or undefined. And those are the places where we can have relative maximums or relative minimums. Now, it's very important that you understand in this definition, if it has a relative maximum or minimum, then it's a critical number. It is not true to say that if it's a critical number, there will be a relative maximum or minimum. Okay? You can't switch the if-then parts of this statement. I'll show you in an example a little bit later in this lesson where we have a critical number, but we do not have a maximum or a minimum. But what this does for us is it says if we're looking for these maximum or minimum points, they have to occur at critical numbers. They can't occur anywhere else. So if we find our critical numbers, we're going to reduce down the number of possible places that we could have a relative minimum or a relative maximum. I hope that you're beginning to get the idea of kind of what we're talking about here. If we're looking for a maximum or a minimum of a function, and I might just point out there's lots of situations where we might want to do that. For example, in business, if we have a profit equation, we're going to be really interested in where that maximum profit occurs. Or if we have a cost function, we might be really, really interested in where that minimum cost function occurs. So what we want to do is to be able to find those places fairly quickly. We can use critical numbers to narrow down the possibilities, and then we're going to see how we can test to see if indeed we do have a maximum or a minimum. Now, we've covered a lot of definitions and a lot of rules, and I think as we do these examples, you're going to see how these things fit together, and they'll make a little bit more sense to you. Our first example is asking us to find the intervals where f is increasing or decreasing, and then find any relative extrema. So we're going to illustrate that. Now, recall that we want to know, first of all, that this is a continuous function. Well, this is a polynomial function, so it's continuous everywhere. So I'm just going to make a note. This function is continuous all the way from negative infinity to positive infinity. So we're going to follow those steps that we had for a continuous function. We're going to find the critical numbers. Well, in order to find those, we need to have the derivative. So let's get the derivative of this function. F prime of x, this is going to be an easy one, would be 4x cubed minus 4x. Okay? So we're going to put this in a form because what we want to know is where is this derivative equal 0 or where is it undefined? Well, I'm going to make a note first of all that this derivative is defined everywhere. There are no places where it's undefined. So the only thing we're going to be worried about then is where is it equal 0? Well, let's take this and let's do a little factoring. Let's factor 4x out of both of these terms. So let's see, that's going to leave us what? X squared minus 1. So I have 4x times x squared minus 1 equals 0. So if I set this factor equal to 0, I'm going to get x equals 0. If I set x squared minus 1 equals 0 and solve for x squared first and then take the square roots, remember there's 2 square roots, so x is going to be plus or minus 1. Notice another option here is to go ahead and continue to factor. X squared minus 1 is x plus 1 times x minus 1. And notice, again, from this, we're going to get x equals 0, x equal 1, and x equal negative 1. So my critical numbers, I'm going to call those CN. Critical numbers are x equals 0, 1, and negative 1. Now, recall that what we want to do, according to our test here for continuous numbers, use critical numbers to define test intervals. Well, here's how we're going to do that. I'm going to just first of all draw in a number line. You won't need to do this every time, but we're going to locate these critical numbers. Here's 0, here's 1, and here's negative 1. Notice that these critical numbers divide the number line up into several intervals. These are going to be our test intervals. The first one will extend from negative infinity to negative 1. So all of this left-hand side of my number line is one interval. Then we will have another interval between the critical numbers negative 1 and 0. So I'll have this interval. I'll have another interval between the critical numbers 0 and 1. And then finally, I'll have another interval from 1 to infinity because there's not any other critical numbers. Recall that our derivative can only change signs at critical numbers. So on this entire interval, the derivative will always be the same, either positive or negative. Okay? So what we have to do is just choose one arbitrary number. Notice, find the sign of the derivative at an arbitrary point in each test interval. So we're going to do that next. Let's just pick a number in this interval from negative infinity to negative 1. Now you can pick negative 50, negative 2000, whatever. I usually just pick something just so I'm sure it's in the interval. So I'm going to say I'm going to pick the test number negative 2. Okay? Test number. We're going to check the sign of our derivative at that test number. Now you can do that two different ways. You can substitute this test number into your derivative right here. Sometimes that's a little bit hard. I'm going to show you another way that I think is a little bit easier. I'm going to come down here to this factored form of our derivative. Notice if I take the test number negative 2 and substitute it for x here, 4 times negative 2 would be a negative number. If I put negative 2 here, negative 2 plus 1 would be a negative number. Negative 2 minus 1 would be a negative number. In other words, using the test number negative 2, all three of these factors would be negative. Now what happens when you multiply three negatives together? Well, you get a negative answer, don't you? So on this interval, because my test number gave me a negative value for my first derivative, all of the numbers in this interval would give me negative values for my first derivative. Okay? Now, between negative 1 and 0, we can use the test number negative 1/2, let's say. Now, the good news is we don't have to exactly evaluate this derivative. We just need to determine, is it positive or is it negative? So again, let's go to these factors down here. 4 times negative 1/2, my test number, would be negative. Negative 1/2 plus 1 would be positive, wouldn't it? Negative 1/2 minus 1, again, would be negative. What happens if you multiply two negatives times a positive? That end result is going to be positive, isn't it? Okay? So for every number between negative 1 and 0, my derivative is going to be positive. Okay, let's move to the next interval. Between 0 and 1, I can use the test number 1/2. So again, let's go to these factors. 4 times 1/2 is positive. 1/2 plus 1 is positive. 1/2 minus 1 is negative. If I multiply two positives times a negative, I'm going to get a negative answer. Okay, we've got one last interval. From 1 to infinity, we can choose anything. I'm just going to use the test number 2. 4 times 2 is positive. 2 plus 1 is positive. 2 minus 1 is positive. The product of three positives is positive, isn't it? Now, what we have discovered here is for all of the x values between negative infinity and negative 1, my first derivative is negative, which says my function is decreasing. On this second interval, we found that between x equal negative 1 and x equals 0, my first derivative is positive, so I'm increasing on that interval. Again, my derivative went to negative, so in this interval from 0 to 1, we're decreasing. And finally, then we're increasing again. Now, I'm not going to exactly sketch, but what we have shown here, let me, and I don't know what these values are just yet, but when I get to this x value of negative 1, my curve is decreasing. It's coming down somehow, okay? When I get to this x value of negative 1, my curve starts to increase. So it's going to come down, it's going to start increasing. When it gets to this x value of 0, it changes from increasing back to decreasing, okay? And then when it gets to an x value of 1, it starts increasing again. So it was decreasing, increasing, decreasing, increasing. Notice where we changed from decreasing to increasing, we went through a low point. Decreasing to increasing. So we have a relative minimum, a low point, at x equal negative 1. We went from increasing to decreasing, so we had a high point. So we have a relative maximum at x equals 0. Then again, we went from decreasing to increasing, so from down to up, we went through another low point at x equal 1. Now, sometimes you want to know not only where these extrema happen, but what the value is. Now, I have a relative minimum at x equal negative 1. If I want to know the actual point on the graph, I need the y value that goes with that, don't I? Well, the place you find y, remember, is back up here. F of x is the same thing as y. The mistake that some students make is they take this value and they put it in the derivative. That's not what we want. I want the y value that goes with x equal negative 1. Well, notice if I put negative 1 in both of these places, since we're raising to an even power, those will become positive 1s, won't they? So I'll have 1 minus 2 is a negative 1. So at negative 1, negative 1, I have a minimum. Okay? Then at x equal 1, 1 minus 2 would be negative 1. There's another minimum. At x equals 0, notice if x is 0, those are both 0, so 0, 0 is a maximum. So my minimum occurs at x equal negative 1. The minimum value is negative 1. I have a minimum at x equal 1. The minimum value is negative 1. And I have a maximum at 0, 0. Now, this was just kind of an illustration in terms of how the curve was shaped. But notice with this information, I can get a little bit more technical. I notice at 0, 0, I have a maximum. At negative 1, let's say right there, I have a minimum. So my curve is decreasing to that point, comes up to there. At 1, negative 1, I have another minimum. So it's going to come down there and down there. Now, we will explore later the exact shape in between here, but I know I have these two low points and this exact high point. And so I know roughly what my curve looks like. We have a theorem called the first derivative test. If f is continuous on an open interval containing the critical number c, if the derivative changes from negative to positive at c, then f of c is a relative minimum. Negative to positive says you go from decreasing to increasing, so you went through a low point, a minimum. If the derivative changes from positive to negative, goes from increasing to decreasing, then we have a maximum. F of c is a maximum. If the derivative does not change sign at c, then f of c is neither a minimum or a maximum. Okay? Notice the y value is referred to as the minimum or the maximum. Find the intervals where f is increasing or decreasing and find any relative extrema like we did a while ago. Now this involves a trig function. Notice also we've got a restricted interval. Here, you know the cosine graph, how that sort of is periodic. We're only going to concern ourselves between 0 and 2 pi. So the first thing again, our function is continuous on this interval. So we have a continuous function. And we need our derivative so we can get these critical values. Now, some students have a hard time with this, so I just want to point out that x over 2 is the same thing as 1/2 times x, isn't it? So the derivative of x over 2 is just like taking the derivative of 1/2 times x. That's going to be 1/2. The derivative of the cosine is what? Negative sine, isn't it? So minus negative sine x. I'm going to put that in for emphasis. The derivative of x over 2 is 1/2 minus the derivative of cosine is negative sine. I'm going to rewrite this now as 1/2 plus the sine of x. Now remember, we want to know where is this equals 0 so we can find our critical values. Notice it's defined everywhere. Okay, if we solve this equation, sine x would equal negative 1/2. Just taking that over. Where is the sign negative 1/2? Well, let's think about, first of all, the sign is negative in quadrants 3 and 4. So we know our critical value will be there. Now, we can use as a reference the angle whose sine is positive 1/2. Now I'm going to do a little review here from your trig. Recall if you have your 30-60 triangle, the side opposite 30 is 1, the hypotenuse is 2, and square root 3 is opposite 60. The sine of 30 is 1/2. So 30 degrees, which is pi over 6, is our reference. Now we have to use real numbers here. We can't use degrees in this calculus thing. So pi over 6 is our reference. So if we go to quadrant 3 and use a reference of pi over 6, well, let's think. This is pi right here. So pi plus pi over 6 is going to be what? 7 pi over 6. So one of my critical numbers is x equals 7 pi over 6. If we go to the fourth quadrant with pi over 6 as a reference, remember this is 2 pi. 2 pi is 12 pi over 6, isn't it? So if we like pi over 6 getting there, my second critical number is going to be 11 pi over 6. Okay? So, since we're restricted between 0 and 2 pi, we're going to set up a test interval from 0 to this first critical number of 7 pi over 6. Okay? Then we're going to go from the 7 pi over 6 to the second critical number of 11 pi over 6. And finally, we'll go from the 11 pi over 6 up to 2 pi. These are our test intervals. And recall, what we want to look at here is the sign of our derivative. Okay? Here's our derivative right here. That's what we'll be using. Well, now, we can pick anything between 0 and 7 pi over 6, so let's pick something really, really easy. For example, pi is between there, isn't it? If I put pi in place of x, the sign of pi is 0. 1/2 plus 0 is 1/2, which is positive. Okay? So I know my function is increasing here. Between 7 pi over 6 and 11 pi over 6, we could use 3 pi over 2. Okay, recall at 3 pi over 2, the sign is negative 1. 1/2 plus a negative 1 would be negative, and we're decreasing. Okay? And then finally, between 11 pi over 6 and 2 pi, we could pick some value in there. Remember, pi over 6 is like 30 degrees, so we're just 30 degrees below. So if we drop 15 degrees below or something like that, we can get the value there. So if we do that value and put it in, we're going to get a positive, and we are increasing again. So I go from increasing to decreasing to increasing. So if I go from increasing to decreasing, I have a relative maximum at x equal 7 pi over 6. And I have a relative minimum, because I go from decreasing to increasing, at x equal 11 pi. Oops, I forgot my pi. 11 pi over 6. Now, if we want the y values that go with these, what do? We go back to the original function. So, like for the y value here, y would equal 7 pi over 6 times a half, because x over 2 is like 1/2 times x, minus the cosine of 7 pi over 6. What I would suggest is that you just go to a calculator and approximate that value to get those y values. Now, I'm going to leave that for an exercise for you because this lesson is going to be long enough as it is. The important thing is that you understand how to find your critical values, set up your test intervals, pick a test number in each interval, find the sign of your derivative, see whether it's increasing or decreasing, and then based on that, you can determine any of these relative minimums or maximums. Okay? Find the intervals where f is increasing or decreasing, find any relative extrema. So we're going to do the same thing. Now, let's talk about this 2/3 power. Remember, that means cube root raised to the 2nd power. That's important. A cube root can be found for any positive or any negative number. So that means that this function is continuous everywhere. There's not going to be any problem with finding cube roots. Okay? So let's get our derivative. Our derivative, let's see, 2/3 would come down. X squared minus 9. If we subtract 1 from that exponent, we're going to get negative 1/3. And then don't forget the chain rule. Go inside here. The derivative inside is 2x. Okay, let's rewrite this just a little bit. Because of this negative power, we're going to slide that underneath. So the 2 times the 2x will be left on top. The 3 is already down there, and then we're going to bring this down, x squared minus 9 to the positive 1/3. Finally, I'm just going to go ahead and write that as 4x over 3 times x squared minus 9 to the 1/3 power. Now, don't forget, critical numbers are numbers that will make our derivative equal 0 or undefined. This is the first time that we're going to have critical numbers that result from our derivative being undefined. Notice, first of all, if you say, what's going to make this equal 0? If you have a fraction that is equal to 0, it's the numerator that must be 0. So 4x equals 0 gives us x equals 0 for a critical number. Since this is a fraction, if the denominator becomes 0, then it's undefined, isn't it? So if x squared minus 9 becomes 0, then this whole thing becomes 0 and we are undefined. So x squared would equal 9, which means x is plus or minus 3. These are also critical numbers. Now keep in mind, our original function is defined at these values, but our derivative is not. Okay? Now, we have critical numbers of 0, positive 3, and negative 3. Again, kind of think mentally on a number line. Starting from negative infinity, my first critical number would occur at negative 3, and then continuing to the left. Negative 3, my next critical number is 0. And then 0 to my next critical number of positive 3, and finally positive 3 to infinity. If you have trouble seeing those intervals, you might want to actually draw the number line and place them on there. Now again, remember, we're looking for the sign of my first derivative. Okay, well, let's get a test number here. To the left of negative 3, anything to the left of negative 3. Let's just say we're going to use a negative 4. We're going to go back to our derivative in this form right here. Notice if x is negative 4, our test number for this interval, my numerator would be negative, wouldn't it? 4 times negative 4 is negative. Now, down here in the denominator, negative 4 squared is a 16. 16 minus 9 is positive. The cube root of a positive is positive. 3 times that positive would be positive. So I'd have a negative over a positive, which gives me a negative value, and I know my curve is decreasing. Okay, between negative 3 and 0, I could use the number negative 2. Well, 4 times negative 2, that's negative. Negative 2 squared is a 4. 4 minus 9 is a negative number. The cube root of a negative number is negative. And 3 times that negative would be negative. So I have a negative over a negative is a positive, and we're increasing. Between 0 and 3, I can use a 2. 4 times 2, that's 8. That's positive. 2 squared is 4. Minus 9 is negative. The cube root of that negative is negative. 3 times that would be negative. So I'll get a negative decreasing. And finally, in this interval, we can use positive 4. 4 times positive 4 is positive. 4 squared is 16. Minus 9, that's positive. So all this stuff is going to be positive. And we're increasing again. Now, I just want to mention right quick, on every one of these examples, we've always alternated, decreasing, increasing, or whatever. That doesn't always happen. So don't get lulled into thinking that that will always be the case and start cheating and only check this one and then alternate. I'll show you in a little bit. We're going to have an example where that won't work. Okay, so we know where we're decreasing and increasing and so forth. Let's find these relative extrema. I go from decreasing to increasing. Decreasing to increasing, that says I went through a relative minimum. So I have a relative minimum at x equal negative 3. Increasing to decreasing. So I had a relative maximum. I went through a high point at x equal 0, because 0 is where I changed. Decreasing to increasing, I changed at 3. Decreasing to increasing, and went through another minimum at x equal 3. Now I'm going to go ahead and find the actual values on this one since it's a little bit easier than that last example. Notice that if x is negative 3, if you come back up here, negative 3 squared is 9. 9 minus 9 is 0. So we have a relative minimum at the point negative 3, 0. Notice also if x is 3, 3 squared is 9, minus 9, that's 0. So we also have one at 3, 0. I have a relative maximum at x equals 0. Okay, 0 minus 9, that's a negative 9, isn't it? So I'm going to have the cube root of negative 9 squared. Okay, so I'm just going to write it in that form. If you have a calculator, you can evaluate that. Okay, I do know it's going to be a positive answer. Notice you're squaring this negative number, so you're going to get a positive answer. Now, I want to talk a little bit about the shape of this thing. I know at x equal negative 3, I'm on 0. At x equal positive 3, I'm on 0. At x equals 0, I'm up here on some positive value. Okay. This curve decreases to here. It increases, decreases again to here, and then increases again. I've drawn this way. Now, as I said earlier, we're going to find some things to tell me exactly how I know it's shaped this way. Notice how this comes down and has a cusp, makes a sharp curve back. See, one hint that that's going to happen is because at x equal negative 3 and positive 3, my derivative is undefined. So it doesn't make a smooth transition like it does at 0. There's a horizontal tangent line here. There's no tangent line here and here. So it's got to be a sharp corner at those places. Find the intervals where f is increasing or decreasing and find any relative extrema. I did this example mainly because I wanted you to see that things don't always alternate like we talked about earlier. Notice this again is a continuous function everywhere. Our derivative is 5x to the 4th. Again, that's defined everywhere. If we ask ourselves, where is this equal 0? Well, that's pretty obvious. X has to be 0, doesn't it? That is our only critical number. So from negative infinity, we go to the critical number 0, and from the critical number 0, we go to positive infinity. And we're going to look at our derivative. Notice if you pick a test number here, say negative 1, and you put it in your derivative right here, negative 1 to the 4th is a positive answer. 5 times that's positive. I'm increasing. From 0 to infinity, pick say a positive 1. Put that in, everything's positive. Increasing. This function turns out to be always increasing. I could tell that right here. 5x to the 4th, this derivative is always positive, isn't it? So my curve has to always be increasing. Now, this is a situation where even though I had a critical number, I did not change from increasing to decreasing or vice versa. There is no relative maximums or minimums, no relative extrema here, because I don't change from increasing to decreasing or decreasing to increasing. So again, that points out that if you have a relative extrema, it has to be at a critical number, but there can be critical numbers where there's no relative extrema. Actually, this graph looks a lot like y equal x cubed. It does something like this. So it sort of levels off in here, but it increases the whole way, moving from left to right. We're always going up, and there's no minimums or maximums here. Now, what about discontinuous functions? Everything we've done so far has talked about continuous functions. So what do we do if we have a discontinuous function? If f is discontinuous, then the derivative can change sign at critical numbers or at points of discontinuity. Therefore, we will use critical numbers and points of discontinuity to define test intervals. We will find the sign of the derivative f prime at an arbitrary point in each test interval, just like we did before, to determine whether f is increasing or decreasing. Let me just, on the back of this, show you right quickly. You're familiar with graphs of functions where you have an asymptote or something. Let's say we've got a graph that does this, and on this side it does this. Notice my graph is increasing here, but here it's decreasing. It's undefined. There's a vertical asymptote right here. It's undefined at that vertical asymptote. But it changes from increasing to decreasing, not at a point on the graph, but rather at that vertical asymptote, at a point of discontinuity. So that's the reason that we use not only critical numbers, but also discontinuous points to define our test intervals. Find the intervals where f is increasing or decreasing and find any relative extrema. Okay? Well, let's notice first of all that this function is discontinuous at x equal negative 1. How do I know that? Because negative 1 plus 1 produces a 0 in the denominator. So this function is not defined at x equal negative 1. We have a discontinuity there. Recall that if a value of x makes the denominator 0, but it does not make the numerator 0, then it's a vertical asymptote. Negative 1 makes the denominator 0, but it does not make the numerator 0. So I know that I have a vertical asymptote at x equal negative 1. Okay? Now, let's go about finding our critical values. We're going to get the derivative here. We'll need the quotient rule to get our derivative. Denominator x plus 1 times the derivative of the numerator, 2x, minus the numerator x squared times the derivative of the denominator, that's 1, over the denominator squared. Now, the main thing you've got to be careful here is that not only can you do that quotient rule, but that you can simplify correctly. A lot of students want to cancel this x minus 1 with one of these down here. Can't do that. Notice that subtract sign right there. X plus 1 is a factor of this first term, but it's not in the second term, so it's not a factor of the whole thing, thus you can't reduce it here. So all we can do is multiply this out and simplify on top. So distributing our 2x here, 2x times x gives me 2x squared plus 2x times 1, so plus 2x. And then I have a minus x squared. Again, all of this is over x plus 1 quantity squared. And finally, combining like terms, I have 1x squared, so x squared minus 2x over x plus 1 quantity squared. And then I'm going to do one other little thing here. Oh, I just made a mistake. That's x squared plus, I knew something was wrong there. X squared plus 2x. I was writing a minus. I'm not sure why. Plus 2x times 1. That's a plus 2x. Just miscopied. You need to really watch that. Don't be like me and nearly make a careless mistake, because that would mess us up. I'm going to factor this numerator. I can factor an x out. X times x plus 2 over x plus 1 quantity squared. Okay, now remember, critical numbers are values of x that make our derivative equal 0 or undefined. Well, obviously, down here in the denominator, if x is negative 1, I get a 0 in the denominator, and so my derivative would be undefined. So I'm going to include negative 1 as a critical number. Okay? Up here, if I say, what's going to make this equal 0? Okay? Alright. Since this is factored, if my fraction is equal 0, remember it's the numerator. X equals 0 would make it 0, and negative 2 would make it 0. Negative 2 plus 2 is a 0. So I have a critical number of 0 and negative 2. Now, let me come back and talk just a little bit technically here. I included negative 1 as a critical number because the derivative is undefined there. However, my original function is also undefined there. So according to the technical definition, that is not a critical number per se. We can't have a minimum or a maximum there because my function is not defined there. Okay? But when we set up our test intervals, recall on this discontinuous function thing, we're not only going to use critical numbers, but we're also going to use points of discontinuity. So, although negative 1 is not technically a critical number, it is a point of discontinuity, so it will be used to set up our test intervals. So, let's see. Starting from the left, moving to the right, my first critical number would be at negative 2. And then I would move from negative 2 to this point of discontinuity, negative 1. I would move from the point of discontinuity, negative 1, to the critical number 0. I would move from 0 to either my next critical number of point of discontinuity. Well, I've used my 0 right here, I've used my negative 2 right here, and I've used my discontinuity negative 1, so there's not another one, so that means that goes to infinity, doesn't it? Remember, we're looking at the sign of f prime on each of these intervals. The best place to go is this final little factored form right here. What is the sign of the derivative? Well, let's pick a test number here. Let's say negative 3. Well, this factor would be negative if x is negative 3. Negative 3 plus 2 would also be negative, wouldn't it? Negative 3 plus 1 is negative, but notice we're squaring that, so the denominator would be positive. In fact, the denominator's always positive, isn't it? Anything squared is positive. So if I have the product of two negatives, that would be a positive, divided by a positive, gives me a positive answer for my derivative. I'm increasing. Between negative 2 and negative 1, I can use negative 1 1/2. Well, if x is negative 1 1/2, that's still negative right there. Negative 1 1/2 plus 2 is positive. And we've already said this thing down here is always going to be positive because we're squaring it. So a negative times a positive is negative, divided by a positive gives me a negative answer. I'm decreasing. Okay? Between negative 1 and 0, I can use 1/2. I'm sorry, I can use negative 1/2. Well, negative 1/2 makes that negative. Negative 1/2 plus 2, that's positive. This is positive, so I get a negative divided by a positive. That's still negative, still decreasing. And then finally, from 0 to infinity, if I use a positive number, that's positive, this is positive. So since everything's positive, I'd have a positive answer, and I'm increasing. Now, notice at this x equal -1, that's where my vertical asymptote is. But I went from increasing to decreasing, so I had a relative maximum at x equal -2. Now I'm going to go ahead and put the x value of -2, and we're going to find the y value that goes with that. -2 squared would be